In section 2.8 of the text, and we're doing number 3 of the exercises, and it says compute the following limits using the Hopital's rule if you can, basically. So first we've got to see if we can. If we put in 0, cosine of 7 times 0 is 0. Cosine of 0 is 1. And this would be cosine of 0, also 1. And we get 1 minus 1, which is 0. The numerator is headed to 0. The denominator is also headed to 0. And if they both go to 0 or both go to 1, or infinity, then L'Hopital's rule works. And so we can say this will be have the same limit as x approaches 0 of the derivative of the numerator. Derivative of 1 is 0, and the derivative of cosine is negative sine. We have a negative already, so it will be plus sine of what's inside times the derivative of the inside, which there's a 7 there. And the denominator will be similar, plus 3 sine 3x. Now, if x goes to 0, sine of 0 is 0 times 7 is 0, so this goes to 0, and this will go to 0, so both of these still go to 0. So I can do L'Hopital's rule again, and I get the limit as x approaches 0 of, so I have a 7, that's a constant, and then I can take the derivative of the sine. The derivative of the sine is the cosine of 7x, but the derivative of the inside is also a 7, like it was the first time. So I get another 7. And in the denominator, I have the 3, and the derivative of the inside produces another 3, and the derivative of the sine is cosine. And now as x goes to 0, cosine of 0 goes to 1. This goes to 1. And so I get 7 times 7 times 1, 49. And 3 times 3 is 9 times 1 is 9. Okay, number 2. Or part 2 of this number 3. As x goes to 1, well, 4 to the 1 is 4. 3 to the 1 is 3, so 4 minus 3 is 1 minus 1. Oh, the numerator goes to 0. 1 squared is 1 minus 1. It goes to 0. So L'Hopital's rule applies. So this becomes the limit as x approaches 1. The derivative of 4 to the x is ln 4 times 4 to the x, minus the derivative of 3 to the x is ln 3 times 3 to the x, and the derivative of 1 is 0, over derivative of x squared is 2x, the derivative of minus 1 is 0. Now as x goes to 1, this will get close to 2, and this will not be 0, so I'm going to get out of this, 4 to the 1 is 4, so I'm going to get 4 ln 4 minus, and this will be 3 to the 1, which is 3 ln 3, over 2, and I can work out a decimal for that, but that's basically what you got to do for that one. Let's look at number 5. So number 5, bring it down here a little bit. It says f and g are differentiable functions. F and g look like at 3 are 0. Their slopes are 0, and their second derivatives are not. Let a new function h be their quotient. On the same set of axes, sketch the possible graphs of f near and g. Possible graphs of f and g near 3. So here's 1, 2, 3, and the height of f and the height of g are both 0. The slopes of both of them are 0. And the second derivative, saying the curvature is negative on f, so it's curved down. So that could be f, slope of 0, height of 0. And g has a curvature of 1, so it's curved up. That's kind of what the picture looks like. Use the provided information to determine the value of the limit of this quotient. Well, since both of them are going to 0, this is f of x over g of x, and as you get close to 3, they both go to 0. So we can do the limit as x approaches 3 of their derivatives. Well, f prime of 3 and g prime of 3 are still both going to 0. So we can do Hopital's rule again, and it would be the limit as x approaches 3 of the second derivative, which would be f double prime of 3 over g double prime of 3, and that turns out to be negative 2 over 1. Okay, and I've kind of explained as I've gone along. Okay. 6. Find all the vertical and horizontal asymptotes. Well, if we have a factor that's the same in the numerator and denominator, generally they cancel out, but we don't get exactly the same function. We get a similar function that doesn't have this feature. You can't use a in this, but if you cancel them, you get 3 times x minus b over 3 times x minus c. And this is very similar, except it doesn't have the hole. That's what is caused by this. This is very smooth connected, except at C. And so the graph of this, what is it going to look like? Well, at C, so let's just say C was here, this is going to have a vertical asymptote. And since it happens at only once, it's not squared or cubed or anything, then the actual curve has to go in opposite directions as you approach it. If it was squared, they'd both go either up or asymptotically down. Okay? So at C, they go in the same opposite directions. And let's see what else we know. At B, if x was B, wherever B is, this whole fraction would be 0. So if B is over here, it would be 0. And so the curve would have to go like this. If B was on this side someplace, then it would have to go like this. So let's say B's there, C's there, and A, wherever A is, let's say A was here, and if it goes like this, on the other side it would have to go like this, and horizontally, since this is going to have x squared and x squared, horizontally the asymptote is going to be 3/5, because it goes by the leading coefficients. This would be 3x squared plus some ax's and bx's, and this will be 5x squared. And so these are equal in power, so it's going to make a horizontal asymptote of 3. You can also show that by doing Hopital's rule. As we, let's see, how would we show that? We would take as x goes close to C, nope, this is 5. Sorry, 5 there. Okay, just by the rule we had before, this is going to be 3/5. As x gets really large, this would go to infinity, this would go into infinity, or really small, negative infinity. These would both still go to infinity. So we can do Hopital's rule and take the derivative of the numerator. Well, this is 3x minus 3b, and the derivative would be 3, and the derivative of this would be 5. So if you take the limit as x approaches infinity, either positive or negative, you're going to get 3/5 after doing the Hopital's rule. So the horizontal asymptote is 3/5, and wherever b is, it has to go through 0. If b's here, it's there, or if b's here, it's here. But it has, and then it's asymptotic to c, and it has to go in opposite directions at c. So over here, it would do something like this. And wherever a is, if a was right here, there would be a hole in the graph at a. If a was over here someplace, there would be a hole in this part of the graph. And that's how this one works.